Almost, but not quite forgot.
Yeah, we're glad.
I was given a proctor exam and then looked at the top and it was like a math exam. And I was like, I'm supposed to be.
That's all right. That's all right.
I got the phone call.
Did you? It got crazy, like in the library at the last second.
I did it once this semester, so I can't.
Well, my thing was I was in the middle of doing a project.
I was halfway across campus.
Thank you. Thank you, both of you. Thank you.
Okay.
I don't have a pack, so I didn't know what.
Yeah, one of these.
Which
is,
one's?
that one has 2 bars.
Okay.
That's got 3. Use this one. You're good to go.
This is all we need. It's good.
Yeah, y'all wear too many hats.
I'm serious, I was over there and I did some printing and I'm getting to the exam and looked at the top of the exam and saw math. I was like, oh. It's
Mystery
Okay, good afternoon, everybody. Remember that we do not have class on Monday. All right, so we won't be here on Monday. The last class we had, I was going over that worksheet, so you want to pull that back out. And if you were not here in our class last time and don't have one and need one, you can come up and get it. And we made it through all the way through 5, and I just had number 6 and number 7 left to cover. Okay. All right, so we're going to finish these 2 problems, and then we're going to start with 1.6. 1.6 will be broken up into 2 days. All right, so we'll just do half of 1.6 today, and when we come back on Wednesday, we'll finish up 1.6. So with this last, next to last problem here, number 6, it says, and the hardest part about this problem is even knowing what the picture is supposed to look like, and so that's why I pull it up so that we can do a little sketch. All right. So here with number 6, it says a building is 2 feet from a 9-foot fence that surrounds a property. A worker wants to wash a window in the building 13 foot from the ground. He plans to place a ladder over the fence so it rests against the building. He decides he should place the ladder 8 feet from the fence for stability. To the nearest tenth of foot, how long a ladder will he need? Okay, so the first thing we know is that there is this ladder. I mean a fence. Maybe that'll go away. Okay, there's a fence, and this fence happens to be 9 feet high. Okay, let's see if I can get my pen to be a little thinner. This is a mighty thick pen. You know how to make my pen thinner on this?
Just the down in the corner. No, in the bottom corner, the little pin.
Okay, yes, thank you. Hopefully that'll work. Okay, I don't want you anymore. I don't need you anymore.
Yeah.
Awesome. Whew. Okay, so let's try this again. Oh, well, we're just going to write fat today, okay? There's a 9-foot fence, and there's this building, and the building has a window up here that's 13 feet. That is just bad. Please stay there. Yay. Got it. Yay.
Excuse me.
Yeah, somebody said something.
Yeah, somebody said something.
This is Plymouth. The last one
Yes.
we got was 1.5.
Yes, 1.5 handout, correct?
Yes.
Yes, and I'm still on that same handout. And in the last class we did problems 1 through 5. And so now I'm starting on that same handout. I'm starting number 6. So same
Okay.
handout. All right, thank you for clarifying. Okay, so we have a ladder that is 9 feet tall and a building that is 13 feet. So here you got this building that's up here at 13 feet. All right, so let's see what he does. He says a building is 2 foot from a 9-foot fence. So I didn't even draw that correctly. That's ugly. Here's my 9-foot fence. There's my building, because I have to have 2 feet between my building and my 9-foot fence. There we go. All right. And then it says a worker wants to wash the window, 13 feet for the ground. He plans to place a ladder over the fence so it rests against the building, and he decides he should place that ladder 8 feet from the fence. So here's my ladder, and that's 8 feet from the fence. Okay. So the hardest part of this one is just getting the picture. And actually, this problem came out of your book, and in your book, they even draw the little picture for you, because they know that could be kind of confusing the way it's all worded. But once you get that, it's fairly simple, because you see that you have a right triangle, correct? And the base of it here is going to be 10. The height is going to be 13, and you want to know how long your ladder is. So with a right triangle, you're just doing a squared plus b squared equals c squared. So really this problem was just, let's look at how they set it up. But in the book, they actually gave you the picture of how they set it, of how they have the dimensions. After that, it's fairly simple. Take the square root of each side. And so you're going to get plus or minus 16.4. And since this is the length of a ladder, it has to be the positive 16.4 feet. That's how long the ladder is. Okay. The last problem on this worksheet, you will see this kind of problem in 171, which is the class you're in now. If you take 172, which is the next class, you'll see it similar in there. If you take calculus, you will also see this same kind of problem in calculus. Okay, so you may even see it if you take physics, because it's got some velocity in there. So you can see this kind of problem in many different subjects. So with number 7, it says we have a projectile, and it's launched from ground level with an initial velocity of v0. So where you have that little subscript of a 0, you'll hear me say the word naught. So v0 feet per second. Neglecting air resistance, its height in feet t seconds after launch is given by. So they give us this equation. Notice that it's a quadratic. right? And then beside that, they say, let v sub naught equal 32. I have mentioned before in class that if you have one equation, how many unknowns can you have in that equation? Do you remember? One equation lets you have how many unknowns? 1. If I have 2 unknowns, I'm going to need 2 equations, okay? So ultimately, I can't have V's and T's and S's. I'm only going to be able to have one of those variables. So that's why initially they go ahead and they tell me we're going to let V sub naught be 32. So I'm going to rewrite the equation, and in the place of V sub naught, I'm going to put the number 32. Okay, so now I have T's and S's. So in order to solve this, they're going to still have to tell me the value for either the T or the S. So keep reading. It says, find the times or times, because you may have 2 answers, that the projectile will reach a height of 80 feet. Well, remember when they defined this equation, they said that a projectile is launched from the ground with an initial velocity, neglecting air resistance, its height in feet is given by. So S is representing height, okay? So you might want to make a note of that. S represents height, T represents time. And for A, they said find the time or times that the projectile will reach a height of 80. So they're telling me the value for S. So I'm going to put 80 in the place of S. Now I have one equation with one unknown. It happens to be a quadratic equation, but you know how to solve those. We want to get it set equal to 0. Now you could have, and I probably would if I had thought before I wrote that down, I like for my coefficient of t squared to be positive, not negative. Just, I like it that way. Sometimes I make less mistakes that way. You could have moved everything to the other side if you wanted to, all right? But you're still going to get the same answer. Just be careful with your variables and your signs. So we'll let A be equal to negative 16, B is going to be 32, and C is going to be negative 80. All right, so take the 5 seconds that it takes to write that down, because that way when you're putting it into the quadratic formula, you know you won't make a mistake and forget a negative sign. So I'm going to use the quadratic formula and just type that in, write that down. So minus b plus or minus the square root of b minus 4ac all over 2a. Now what happens when you number crunch that, yeah, that should be a little square right there. When you number crunch that, you're going to get negative 4096 underneath that radical. What kind of number is that? Imaginary. Remember section 1.3 when we had negative numbers underneath our radicals? That's an imaginary number. And remember me talking about graphing things, and does that graph ever cross the x-axis if it's got an imaginary answer? It does not. So this, because this is imaginary, remember you get your little eye, your eye would have to come out. What that means is this rocket, this projectile, never does reach 80 feet. It never does. If I had actually gotten a value, if that wasn't a negative number, then it would have given me the times when that would have happened. But this is telling me that it's not going to happen. So the projectile will not reach 80 feet. Will not. Okay? If it had have been a positive number, remember I'm going to get two answers, right? Because it would have been negative 32 plus something and negative 32 minus something. If it really would be a positive answer, it's because it would hit it on the way up and hit it again on the way down. See that? Okay. So you can have two answers and it makes sense. And you can have no answers and it makes sense. For part B, it says, find the times that the projectile will return to the ground for the given value of v sub naught. So this time, they didn't tell me the value of s, but they did tell me that it was going to return to the ground. So when it's on the ground, what's the value of s? 0. That's right. So same equation, but this time my s value is 0. So this is part B. To solve this, since I can factor out the greatest common factor here, I'm going to do that, and I'm going to take negative 16t out of each term. Okay, so if I take negative 16t out of the first term, what am I left with? T. If I take negative 16t out of the second term, what am I left with? Very good, negative 2. All right, so now I'm back to my product rule. So I can set each of those factors, negative 16t equal to 0, and t minus 2 equal to 0. And I get two answers. Okay, and they both represent time. But if t is equal to 0, that means there's no time. It means I'm starting at the beginning, right? And if t equals 2, that means it has been 2 seconds. And their question was, find the time that the projectile will return to the ground. So the specific answer that they want would be when t is equal to 2. So you would need to say 2 seconds. Okay. Sometimes you may find that there are two answers and one of them is negative and one of them is positive. So obviously if it's negative, time's not going to be negative. That would have not worked. Okay. Now you should be able to do all of 1.5 if you hadn't completed that yet. Okay, so you should be able to do that now. Any questions about either one of those two problems? All right. So now we're going to start with 1.6, and we're going to split this up into 2 days. So 1.6 is going to be dealing with rational equations. That just means equations that have fractions in them. And our strategy is going to be to get rid of the fractions. And so that's when you will find the common denominator. And then because we have an equation, I'll be able to multiply both sides of that equation by the common denominator. And that will get rid of my fractions. Okay, so our steps will be number 1, we'll check for restrictions. And what that means is you look at every denominator And our denominators can never be 0. So a lot of times our denominators will have x's in them. And I never want to have a value for x that would make a denominator 0. Okay, so that's what I mean when I say let's look for restrictions. And then you'll find the common denominator. Then you'll multiply through by that, solve it, and then we'll make sure that none of our possible choices were something that was supposed to be restricted in the beginning. Okay, so the first one I'm going to do is just a very, 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 very simple problem, just so that you have the steps. So this is rational equation. I have fractions. I don't want them. Okay, so we're going to just going through this. You can solve this several ways, but we're going to use these steps. So here first I look at each denominator. There is one that has an x in it, has an x by itself. And so the first thing I know is that x cannot be 0 because that would make that denominator 0. The second step is to find your LCD. So our denominators are going to be much more complicated than this, but you want to, if you can factor any denominator, you'll want to factor them because you need to see all its parts. But for this, my common denominator is going to be 15x. Okay, that's what it would take to find the LCD. And then I'm supposed to multiply every term on both sides of that equation by 15x. So I'm writing every single step down right now. So I would have 15x over 3 plus 15x over 5 equals 15x over x. Okay, showing you every step first. Well, the whole point of having the LCD is because now I'm supposed to be able to get rid of my fractions. Well, remember 3 will go up into 15 5 times, 5 will go into 15 3 times, and here my x's would cancel out. So I have 5x plus 3x equals 15. And then you just solve it. Okay. So there are the steps. And then you look and you say, okay, x is equal to 15 over 8. Check to make sure that's not the restriction. The restriction was it couldn't be 0, so I'm fine. Okay. So that's my answer. You can also always go back and plug 15 over 8 into your original equation to make sure that it makes both sides equal. Okay. So that's the steps. Let's build that and make that a little more complicated. So here we have 3x minus 1 divided by 3, subtract 2x divided by x minus 1 equals x. So all of our denominators are already simplified. I can't factor them. So the first thing is to say, what restrictions do I have? 3 is just 3. But the x minus 1, that cannot be 0. What would make x minus 1 equal to 0? Positive 1. So x cannot be 1. As they get a little more complicated, if you can't just look at it and say what the answer is, you can always come over to the side and write down what that denominator is and say, I don't want that denominator to be 0. And then just solve your little equation. Add 1 to both sides. And that's telling you that x cannot be 1. So you can just take your denominators, set them not equal to 0, and solve. And that tells you what x cannot be. All right. So we found our restriction. And now we need to find our common denominator. Now, on the other side, you just had x. X is not in the denominator, so there was no restrictions on that. Okay? All right, what is my LCD going to be? Am I willing to say? You have to have every factor from every denominator, okay, using its highest power. So when I look at the first fraction, it has a 3, so I've got to use 3. When I look at the next fraction, it has x minus 1. So I have to use x minus 1. And on the other side, it's x over 1. So there you go. So my common denominator is 3 times x minus 1. Now I'm supposed to multiply every term by that denominator, okay? So if I'm going to go every single step, I'm going to write every single step down. Because after this, I'm going to not be writing every single step down. Once you see the pattern, I'm hoping. Remember, the point is because when I do that, I'm supposed to, after this, be able to simplify so that I do not have any fractions. So my 3's cancel, my x minus 1's cancel. Okay. At that point, you're just number crunching your algebra. You're foiling things out, you're paying attention to your signs, and you're solving for x. So here, as I foil this out, I'll have 3x squared minus 4x plus 1 minus 6x equals 3x squared minus 3x. Okay. I want to get all my x's on one side. I've got a quadratic. You want to get it set equal to 0. Notice that when you bring the 3x to the other side, your x squares are going to cancel out. So you're going to be left with 1 minus 10x equals negative 3x. And then move your x over, and you'll have 1 equals 7x. So x is equal to 1/7. That is not a restricted value, so I should be good. All right. Let's look at this one. 3x plus 2 over x minus 2 plus 1 over x equals negative 2 over x squared minus 2x. So when I want to find my restrictions, you want to make sure each denominator is factored. So that's true for the first two on the left-hand side. But on the right-hand side, I need to factor out an x so I can see all the factors there. So finding my restriction says, look at each denominator. Don't let it be 0. So with my first fraction, I have x minus 2. So x cannot be what? 2. With the second one, I have an x, so x cannot be 0, because that would make that denominator 0. And then with the third one, it's made up of the other two, right? The x can't be 0. You look at both parts. This would tell you x cannot be 0. This part would tell you that x cannot be 2. So it's repeating. Okay? So it's still x can't be 2, x can't be 0. So now we want our common denominator. So remember I said you go to each fraction, make sure you write down each factor using its highest power. So a factor right here is going to be the x minus 2. That's from the first one. You need an x from the second one. And when you get to the third one, it's made up of x and x minus 2, so you've already used those, so you don't use them again. Okay. And then we're supposed to multiply by our LCD. All right. So if I were to write this, okay, this is my LCD. So I'm going to say, shoot. There we go. I'm going to say LCD times this one, LCD times that one, LCD times that one. Okay, so I don't have to repeat writing it down. You see what I'm doing? And then we know that the x minus 2's would cancel out, but what would I have extra there? Can you see what I would have? X, thank you. That's right, I would have x. So I would have an x for the first one because my x minus 2's would cancel out, so I'd have x times 3x plus 2. For the second one, the x's would cancel out, and I would still have the x minus 2 times that 1. And then for the last one, both the x and the x minus 2 cancels out, so I'm just left with the negative 2. When you are doing some of your review and you're adding fractions and you have to get your common denominator, you weren't able to get rid of the fact that they were fractions. So it's nice when you have an equation that you can find that LCD and just multiply through there. And you can't do that if there's no equals. Okay, we can do that because there's an equals. All right, so this is going to give me 3x squared plus 3x equals 0 when you go ahead and just simplify that. I'm going to factor out what I have in common, which is a 3x. So that leaves me with an x plus a 1. And I'm going to have two choices, 0 or a negative 1. Could be both. They could both be answers. But if we look back at our restrictions in the very first step, remember x couldn't be 0, right? So the only choice is that x is a negative 1. So it is possible for both of your answers to not work out and you say I have no solution. It's possible for both of them to work and you have 2. It's possible to just get 1. Okay. I'm going to give you one that's just a little more complicated. I'm going to give you just a little bit to see if you can find the LCD. So here's our problem that we're going to do. Okay, so you're going to need to factor each denominator, decide what all the restrictions are, and then choose your LCD. Okay, so you've got 3 over x squared plus x minus 2. You've got 1 over x squared minus 1. And you have 7 over 2x squared plus 6x plus 4. So take a minute, factor each of those, find your restrictions, and find your LCD. You got what? Nope, you got a 2. Okay, so you factor each of those denominators. The first one, fairly straightforward, quick, x minus 1 times x plus 2. The second one, you needed to remember that that's the difference of 2 squares. Remember that number 1, they'll play with it because 1 can be 1 squared if you need it for the difference of 2 squares. It can be 1 cubed if you need it for the difference or sum of cubes. So watch out for that. And then the third one, always factor out your common factor if you can. So I factored out the 2 first and then continued on to factor. Look back at each factor to say, what can x not be? So from this first one, x could not be 1. X could not be negative 2. X cannot be 1. We already said that. X cannot be negative 1. So that's a new restriction. And then over here, x cannot be negative 1 and x cannot be negative 2. So you have 3 things. 1, positive 1, negative 1, and negative 2 that x cannot be. Then you need your LCD. So that's the next thing. So you start by writing each factor. So I know I'm going to need an x minus 1. I'm going to need an x plus 2. That came from the first fraction. From the second fraction, I already have the x minus 1. And it's raised to the first power. So there's nothing extra there. But I don't have the x plus 1. So I'd write that one down. Then go to the third. And it has a 2. I haven't used a 2 yet, so I need a 2. But I've already used the x plus 1 and the x plus 2. So that's your LCD. Any questions about so far in that problem? So just be very careful. All right, so now we're supposed to multiply every term.
Excuse me.
Yes.
Madam Mesquite has a question over here. They're lost in somewhere, I guess, in your background.
Okay. Awesome. Okay, so I'll go back and factor each one of those. So this was the denominator on the first fraction. So what I'm going to do there is just use trial and error. So I know that it's going to be x times an x, and then I need to come up with 2 numbers that multiply to be a negative 2, but add to be a positive 1. So that's how I came up with a negative 1 and a positive 2. Okay. That was the first denominator. The second denominator was x squared minus 1. There's only 2 terms there. When there are only 2 terms, you always say, is there something I could take out? And there's nothing that x squared and 1 have in common. Then you start looking for special cases. And since it has an x squared, I want to know, is this the difference of 2 squares? And yes, it is, because that's x squared minus 1 squared, because 1 squared is another way to write the number 1. So you have to remember that a plus b times a minus b is equal to a squared minus b squared. So I'm using that. So this means that this is going to be x plus 1 times x minus 1. So that's the factoring, the second one. And then the third. The third one is 2x squared plus 6x plus 4. Always look to see if there's something that they all have in common that you can take out. A, because you have to. B, because it'll make your numbers smaller and easier for you to factor. So 2, 6, and 4 have 2 in common. So I'm going to factor a 2 out of each term. Then I'm just looking at that trinomial. Now it's more like what I originally started with, one that I can use trial and error on quite easily because the coefficient of x squared is 1. So this time, I need 2 numbers that are going to multiply to give me 2, but add to give me 3. And that's a 2 and a 1. So that's how I factored each of those. Does that help, Madam Mesquite?
Yes, ma'am. Thank you.
You're welcome. All right, so once we've done that, and we factored it, and we found our LCD, now remember we're going to take and multiply the LCD by every single term in our problem. So I'm going to come back and multiply this one by my LCD, this one by my LCD, and this one by my LCD. Okay? And that's going to get rid of all those denominators. When I do that, this is what you're left with. So it looked really complicated in the beginning, but once you multiply by the LCD, all those factors cancel out, and it makes it way simpler to solve. Simpler word, much more simple to solve. So then you just multiply, combine like terms. And when you solve that, you will find that x is equal to 3. 3 was not one of my restrictions, so I'm good. Okay. All right. The very last thing that we're going to look at is in your homework. The very last few problems are called work problems or work rate problems. And just like I have a table for the other types of problems, I created a quick little table for this, and if you substitute your information in, it'll spit it out to you most every single time. All right, so what you're going to do is at the top, you're going to have time to do the job, and the other column will be the amount of the job done in 1 hour. And it's usually something that like Bill paints the room in 5 hours, John paints the room in 3 hours. How long would it take them to paint it together? Okay, so that's why I just call it number 1, number 2, and together. All right. Or a pump is pumping water in and another pump is pumping water out. If they're both going at the same time, how long is it going to take it to fill the pool? Okay. So that's the setup of what these types of problems are. This problem that I'm going to do first, if you want to refer back to it, it's on page 147 of your book, and I think it's number 37. So I am going to take and write down the shorthand version of the question, but if you want to refer to it, it's on page 147, number 37. All right, so we've got Joe, and he's going to paint a room. He's going to paint a house. Paint a house in 3 hours, so it's a little house. And Sam, he's going to paint the same house, because it wouldn't be fair if he was painting a different house. But he can do it, takes him 5 hours. How long does it take them together? So make your little chart, but instead of number 1, number 2, have a Joe and a Sam. So you'll need a column for time to do the job. Basically, that's time to do the job alone. And then the amount of job done in 1 hour. That's your columns. So we're just going to fill in these columns and these rows. So for Joe, it takes him 3 hours, and it takes Sam 5. And that's the question. How long does it take them to do it together? If Joe can do the entire job in 3 hours, how much of the job has he done in 1 hour? A third. So same thing with Sam. In 1 hour, he's done a fifth of the job. And if they were working together, however long it took, it would be 1 over X. That's the amount they've done. So in 1 hour, see, I had to reduce everybody down to, like, you know how if you're dealing with feet and inches, you're not going to add those. Everybody's got to be feet or everybody's got to be inches. You want it in the same unit. So I got everybody to look at what happened in 1 hour. So if they're working together, Joe's amount plus Sam's amount will equal the together amount. So here is where my equation will come from. 1/3 plus 1/5 equals 1 over X, which is the first problem I did in class today. 1/3 plus 1/5 equals 1 over X. Okay, so that's you have that in your notes already. We did that in class. So just to remind you, that's 5X plus 3X equals 15. And this is, remember, we got X was 15 over 8, which you could write as 1 7/8 of an hour. Again, for this answer, I would pay attention to how My Math Lab is asking you to type it in. If you're not sure, click Show Me an Example, go all the way down to the bottom, see how they leave their answer. All right? Yes? They're called like work rate problems. And the only other type of problem that's similar but just got a little tweak is the pipe problem, where you have one pipe that's pouring into a pool and the other pipe that's taking away. Well, then instead of adding, my pouring in would be a positive, but my taking away would be negative. Okay, so that's the only tweak to that at all. All right, so this is Friday. Your homework is up in My Math Lab. Do it. Catch up if you're behind. And I do not see you until Wednesday. So have a good Labor Day.